Tonight, we are going to travel somewhere extraordinary. Not across an ocean or over a mountain range. We are going to travel across time itself, deep time. The kind of time that makes centuries feel like seconds and makes a human lifetime feel like the blink of an eye. We're going to spend tonight inside one of the greatest, most fascinating, most beautifully complicated arguments in the history of science. Not an argument full of anger or bitterness, no. This is an argument made of wonder, an argument built from bones buried in stone for 100 million years, from footprints pressed into ancient mud, from teeth locked inside rock formations that no human being will ever fully see. This is the argument about dinosaurs, not just what they looked like, though that alone could fill 1,000 nights of storytelling. But what they really were, how they moved, how they sounded, whether they were warm or cold, whether they were clever or simple. Whether the world we imagine when we close our eyes and picture a Tyrannosaurus rex is anywhere close to the truth. Scientists have been arguing about these questions for nearly 200 years. And here is the beautiful part. They are still arguing. The debate is not over. The mystery is not solved. Every year, somewhere on this planet, someone pulls a new bone from the earth, and everything we thought we knew shifts just a little. So settle in. Let your body sink into whatever comfortable place you found tonight. Let your breathing slow down and deepen. And let me walk you through the greatest unfinished argument in the history of life on Earth. If you enjoy listening to sleepy prehistoric dinosaur stories like this, subscribe. I post stories like this weekly. Imagine, if you will, a quiet English morning in the year 1824. The countryside is green and soft in the way that English countryside tends to be. Rolling hills, hedgerows, damp grass glistening in pale morning light. The air smells of wet earth and distant coal smoke. Somewhere, a crow calls once from the top of an elm tree and then falls silent. In a small study not far from Oxford University, a man named William Buckland is sitting at his desk surrounded by rocks. Not decorative rocks, not pebbles from a garden path. These are enormous, strange, heavy fragments of something that had once been alive. They had been pulled from the limestone quarries of Stonesfield in Oxfordshire, and they had been sitting in various collections for years before anyone quite understood what they were looking at. Buckland understood, or at least he thought he understood. He was looking at the bones of a giant, not a human giant, not a mythological creature, something real, something that had walked the earth millions of years ago on enormous legs, with a jaw full of teeth like serrated blades, with a body so large that when Buckland tried to calculate its size by comparing the bones to living lizards, the numbers became almost too big to believe. He named it Megalosaurus, the great lizard, and with that naming the study of dinosaurs officially began. But here is the thing about beginnings. They are never clean. They never arrive without confusion. Because the moment Buckland published his findings, the argument started. Not a whispered disagreement, not a polite scholarly dispute. A genuine, passionate, career-defining argument about what, exactly, these bones were telling the world. Some of Buckland's colleagues thought he was right. These were the remains of a massive prehistoric reptile, unlike anything alive today. Others were less certain. Could the bones belong to multiple animals? Could the size calculations be trusted? Could a creature this enormous have actually existed? Or was the math somehow wrong? These questions seem simple to us now, sitting here in the present with everything we know. But in 1824, they were genuinely unanswerable with the tools available. There were no computers to run comparisons. There were no databases of bone measurements. There were no museums full of complete dinosaur skeletons to reference. There was just Buckland, his colleagues, a pile of heavy limestone fragments, and a lot of careful, patient argument. Then, just 2 years later, in 1825, a man named Gideon Mantell published a description of another creature. He called it Iguanodon, the iguana tooth. Mantell had been collecting fossils for years, mostly in the countryside of Sussex, and what he found was something that puzzled him deeply. Teeth. Enormous teeth. Far larger than anything from a living reptile, but shaped in a way that reminded him unmistakably of the teeth of a modern iguana. He reasoned, carefully, patiently, through the logic of comparison, that whatever animal these teeth belonged to must have been an herbivore, a plant-eater, a creature the size of something almost unimaginable. and once again, the arguments began. How big was Iguanodon really? Was Mantell's size estimate correct, or was it wildly exaggerated? How did the creature walk, on 4 legs, or 2, or some combination? Where did that strange conical bone fit? Was it a horn on its nose, a spike on its thumb, or something else entirely? That last question, the horn or thumb question, is one of the most charming mistakes in the history of paleontology. For decades, Iguanodon was reconstructed with a horn on its nose, like a strange prehistoric rhinoceros. It was only when more complete skeletons were found in a Belgian coal mine in the 1870s that scientists realized the conical bone was actually a thumb spike, a weapon or a tool on the first digit of the hand. 40 years of argument, 40 years of published papers and museum displays and careful illustrations, all showing an Iguanodon with a horn that wasn't a horn. And then, just like that, the argument shifted. The reconstruction changed. The world of dinosaur science moved on to the next debate. This is how it has always worked. This is how it still works today. Let's stay with the 19th century for a moment longer, because the arguments that happened in those early decades of dinosaur science establish patterns that echo all the way to the present. They established the basic shape of the debate, the way paleontologists think, the way they challenge each other, the way new evidence reshapes old conclusions. In 1842, a British scientist named Richard Owen made a decision that would define the entire field. He had been studying the 3 known prehistoric reptiles, Megalosaurus, Iguanodon, and a third creature called Hylaeosaurus, and he had noticed something that his predecessors had missed. These animals weren't just large lizards, they were fundamentally different from any reptile alive today in one crucial way. Their legs. Modern reptiles, lizards and crocodiles and their relatives hold their legs out to the sides of their bodies. They sprawl. They move in a low, wide, side-to-side shuffle that is inefficient by the standards of warm-blooded animals, but perfectly adequate for creatures that don't need to sustain high activity levels. Their legs splay outward from the hip, and they press their bodies close to the ground. Owen recognized that the creatures he was studying were different. Their leg bones suggested an upright posture, legs positioned directly beneath the body, supporting the animal's weight from below rather than from the sides. This was not the posture of a lizard. This was closer to the posture of a large mammal, or, Owen thought, a large bird. He coined the word dinosauria from the Greek words for terrible and lizard, though the translation terrible lizard is a bit misleading. What Owen really meant was powerful lizard, or awe-inspiring lizard. He was reaching for a word that captured the sense of something magnificent and ancient, and unlike anything still living. And with that naming, a whole new round of arguments began. Were dinosaurs truly different from other reptiles, as Owen claimed? What did their upright posture tell us about their physiology? Were they more active than living reptiles? Were they warmer? Were they in some ways more like us than like a modern crocodile? These questions would take more than a century to even partially answer, and in the meantime, the bones kept coming out of the ground. Through the 1850s and 1860s, the pace of discovery accelerated. Fossils were being found not just in England now, but in Europe and North America. Each new discovery brought new arguments. Each new argument pushed the science forward. Then came the Bone Wars. The Bone Wars is perhaps the most dramatic chapter in the history of paleontology, a period of intense, sometimes bitterly competitive fossil hunting in the American West during the 1870s and 1880s. 2 men drove this period: Othniel Charles Marsh, a professor at Yale, and Edward Drinker Cope, a wealthy amateur naturalist from Philadelphia. These 2 men hated each other. Not with a cold, professional dislike, but with a genuine, burning, all-consuming rivalry that coloured every aspect of their lives for decades. They spied on each other. They bribed each other's workers. They published papers criticising each other's findings with a sharpness that would be considered unprofessional today. They dynamited fossil sites to prevent the other from accessing them. And through all of this spite and rivalry, they discovered an extraordinary number of dinosaurs. Marsh described Stegosaurus, Triceratops, Brontosaurus, and dozens of other species. Cope described Camarasaurus and Quilophysis, and contributed enormously to our understanding of ancient ecosystems. Between them, these 2 men, who could barely stand to be in the same room, laid the foundation for American paleontology. but they also made enormous mistakes. Marsh famously placed the head of Brontosaurus on the wrong body, or rather, the right body with the wrong head. The full story of Brontosaurus is long and winding and genuinely fascinating, but the short version is that the name Brontosaurus was eventually abandoned for decades, replaced by Apatosaurus, because scientists determined that what Marsh thought was a new species was actually a different growth stage of an already named animal. Then, a century later, a detailed computer analysis suggested that Brontosaurus might have been distinct after all, and the name came back from extinction. This is the shape of the argument. Something is named, arguments follow, a conclusion is reached, decades pass, new evidence arrives, the conclusion shifts. Meanwhile, Cope made his own famous blunder. When reconstructing the marine reptile Elasmosaurus, not a dinosaur but closely related to the Mesozoic world, he placed the skull on what he thought was the neck end of the skeleton. Marsh noticed the error. Cope, unwilling to admit the mistake publicly, reportedly attempted to buy back and destroy the original paper. The professional embarrassment was immense, and it is still remembered today as a cautionary tale about the dangers of assumptions in paleontology. Both men died with their rivalries unresolved, their arguments unfinished, their careers brilliant and flawed in equal measure. They left behind collections that still sit in museum drawers and display cases and storage rooms, bones that are still being studied, arguments that are still being had. The early years of dinosaur science were not a steady march toward truth. They were a chaotic, passionate, deeply human scramble through uncertainty. And that scramble never really ended, it just got more sophisticated. Let your mind rest on this image for a moment. Two men, bitter rivals, crawling through the dust of Wyoming and Colorado in the summer heat, each trying to find the next great discovery before the other could. The bones they pulled from the earth were hundreds of millions of years old. The arguments they started are still being had in university lecture halls and museum conference rooms, and dusty field camps in the Badlands today. There is something deeply calming about that continuity. The arguments go on, the science goes on, the wonder goes on, and we are along for all of it. Let your breathing deepen just a little. Let the images soften at the edges. We have many more hours of story ahead of us, and nowhere we need to be except here, in this quiet space, listening. The bones that started everything are still talking. We just have to learn how to listen to them. For nearly a century after Richard Owen named the dinosaurs, there was one assumption so deeply embedded in paleontological thinking that almost no one questioned it. Dinosaurs were cold-blooded. This wasn't a conclusion that had been carefully argued and tested and confirmed. It was an assumption that arrived almost automatically from the fact that dinosaurs were classified as reptiles. And reptiles are cold-blooded. Everyone knows that. A lizard on a rock in the morning sun, waiting for the heat to reach its blood before it can move properly. A crocodile with its vast patient stillness, capable of lying motionless for hours, because it doesn't need to burn fuel the way a warm-blooded animal does. If dinosaurs were reptiles, the logic went, then dinosaurs were cold-blooded. And if they were cold-blooded, certain things followed naturally. They were slow, not necessarily slow in the way a tortoise is slow, but metabolically slow. They didn't need much food. They couldn't sustain long periods of high activity. They were at the mercy of ambient temperature in the way that modern reptiles are, active in the heat, sluggish in the cold. They probably spent a great deal of time lying in the sun, warming up, waiting. This image shaped everything. It shaped how museum displays were designed, with massive sauropods standing in shallow water, because everyone assumed they couldn't support their own weight on land for long periods. It shaped how dinosaur behavior was imagined, as mostly solitary, mostly simple, mostly reactive rather than proactive. It shaped the popular image of dinosaurs as great, slow, lumbering failures, impressive in size but ultimately doomed, destined for extinction because they simply couldn't compete with the warm-blooded mammals that would eventually replace them. For decades, no one seriously challenged this picture. Then, in the late 1960s, a young paleontologist named Robert Bakker started asking questions that made the entire scientific establishment deeply uncomfortable. Bakker was working with John Ostrom at Yale, and Ostrom had just made one of the most significant fossil discoveries of the 20th century. In 1964, in southern Montana, Ostrom's team had found the remains of a small theropod dinosaur, a meat-eating bipedal creature about the size of a large turkey. They named it Deinonychus, meaning terrible claw, for the enormous sickle-shaped talon on each of its hind feet. What Deinonychus suggested about dinosaur behaviour was extraordinary. The foot claw wasn't just large, it was positioned in a way that suggested it was held off the ground during walking, to keep the sharp edge from wearing down. This meant the animal used it as a weapon, driving it into prey with a kicking motion. The skeleton showed powerful muscles, a flexible, balanced body, and bones that suggested an animal capable of sustained, complex movement. This was not the skeleton of something slow and simple. This was the skeleton of a hunter, an active, intelligent, physically capable predator. Ostrom began revising the dinosaur family tree, noticing striking similarities between dinosaur bones and bird bones. He started arguing carefully and with a great deal of supporting evidence that birds were in fact the direct descendants of theropod dinosaurs, that when you watched a sparrow land on a branch outside your window, you were watching a dinosaur. This idea had actually been proposed in the 19th century by the brilliant biologist Thomas Henry Huxley, who noticed the deep similarities between the famous Archaeopteryx fossil, a creature with feathers and wings but also a dinosaur-like skeleton and teeth, and small theropod dinosaurs. But Huxley's idea had been pushed aside, discounted, argued away. Now it was coming back, and with it came Bakker. Bakker took Ostrom's work and extended it in a direction that genuinely shocked the paleontological world. He argued not just that birds were descended from dinosaurs, but that dinosaurs themselves were fundamentally warm-blooded, active, high-energy, metabolically intense animals more like modern birds and mammals than like modern reptiles. He published papers, he gave lectures, he appeared in popular science magazines with arguments that were passionate and specific and backed by a surprising amount of anatomical evidence, and the scientific establishment pushed back hard. The counter-arguments came from multiple directions. Some researchers pointed to bone histology, the internal structure of dinosaur bones, and argued that the growth patterns were more like modern reptiles than like warm-blooded animals. Others pointed to the energetic demands of maintaining a warm-blooded metabolism, and asked how animals as enormous as the great sauropods could possibly have eaten enough to fuel their bodies. Still others argued that Bakker was making the classic mistake of overinterpreting fragmentary evidence, of seeing what he wanted to see in ambiguous data. The debate became one of the defining arguments of late 20th century paleontology. It wasn't just an academic disagreement. It was a fundamental question about the nature of the most famous animals in Earth's history. The answer would reshape every museum display, every nature documentary, every textbook, every image of a dinosaur that had ever been created. And the evidence kept coming in, pulling in multiple directions at once. Bone histology studies became more sophisticated through the 1980s and 1990s. Researchers found that many dinosaur bones showed a type of internal structure called fibrolamellar bone, a pattern of rapid, continuous growth associated in modern animals with warm-blooded species. This was not what you'd expect from a slow-growing, cold-blooded reptile. This looked like the bones of something that grew fast, burned hot, lived actively. But there were complications. Some dinosaurs showed growth rings in their bones, annual rings, like tree rings, suggesting periods of slower growth during certain seasons. Cold-blooded animals show this pattern, but so do some warm-blooded ones. The growth rings weren't definitive proof either way. Then came the nasal turbinate question. Warm-blooded animals have a structure inside their nasal passages called turbinate bones, complex scroll-like structures that help regulate the temperature and moisture of air as it's breathed in. This prevents warm-blooded animals from losing too much heat and moisture through respiration, which is important when your metabolism is running hot all the time. Cold-blooded animals generally don't have turbinates. They don't need them. When researchers looked at the nasal passages of dinosaur skulls, they found ambiguous evidence. Some dinosaurs showed features consistent with having turbinates. Others showed no clear evidence. The interpretation of these structures is genuinely difficult and fiercely argued. Meanwhile, the discovery of feathers changed everything again. Through the 1990s and early 2000s, an extraordinary series of fossils emerged from northeastern China. The Yixian Formation, a sequence of ancient lake sediments in Liaoning province, began yielding dinosaur fossils of a quality that the paleontological world had never seen. Not just bones, but impressions of soft tissue, skin, and in many cases something that looked unmistakably like feathers. These were not the flight feathers of modern birds. In many cases they were simple. Hair-like structures called proto-feathers or filaments. In others they were more complex, branching structures that covered the animal's body in what appeared to be a coat of fuzz. The implications were enormous. Feathers and feather-like structures are, in modern animals, associated with warm-bloodedness. They serve as insulation, a way of keeping body heat in. A cold-blooded animal covered in feathers would have no use for the insulation they provide, because it doesn't generate significant body heat. If dinosaurs had feathers, this strongly suggested they needed that insulation, which strongly suggested they were generating heat to insulate. The cold blood argument was crumbling, but it didn't collapse completely. Because science, when it's working properly, does not simply accept the most dramatic conclusion. It tests and retests and questions and pushes back even against evidence that seems compelling. Some researchers argued that feather-like structures could have served purposes other than insulation, display perhaps, or waterproofing. Some pointed out that we don't know whether the laning dinosaurs were representative of all dinosaurs or just a subset. Some argued that the relationship between feathers and metabolism is more complex than a simple warm equals feathered equation. The arguments continued. They continue today. What has emerged is not a clean victory for either the warm blood or cold blood camp, but something more interesting and more nuanced. The current scientific consensus, and even that phrase requires qualification, because consensus in paleontology is always provisional, is that dinosaurs occupied a metabolic position somewhere between modern reptiles and modern birds and mammals, something called mesothermy, or intermediate metabolism. Rather than being fully ectothermic, relying entirely on external heat sources the way a lizard does, or fully endothermic, generating all their own heat internally the way a bird does, many dinosaurs may have had metabolic rates that were elevated compared to modern reptiles but not quite as high as modern birds. They may have generated some of their own heat, but also been affected by ambient temperature. They may have been able to sustain more activity than a crocodile, but less than an eagle. This is a profoundly unsatisfying conclusion for anyone who wants a clean answer. But it is also, many researchers argue, the most scientifically honest conclusion the current evidence supports. The cold blood argument changed everything it touched. It forced a complete re-evaluation of how dinosaurs moved, how they behaved, how they interacted with their environments, how they competed and hunted and raised their young. Every piece of the puzzle had to be re-examined through the new lens, and what that re-examination revealed was an even more complex, more interesting, more beautifully strange group of animals than anyone had imagined when the first bones came out of the Stonesfield quarry in the 1820s. Let that complexity settle over you for a moment. Let it become a kind of comfort. Because here is what the cold blood debate teaches us. Even the most fundamental questions about the most famous animals in history can remain genuinely open for 100 years, argued and tested and revised by brilliant people without arriving at a clean resolution. And that is not a failure of science. That is science working exactly as it should, carefully, humbly, always following the evidence even when the evidence refuses to give simple answers. The great sauropods that shook the earth with their footsteps, the predators that hunted in ancient forests under skies we'll never see. Were they burning hot inside their enormous bodies? Were they cooler, slower, more patient? The bones say things, but they don't say everything, and perhaps that is exactly as it should be. Rest here for a moment. Feel the weight of ancient mystery settling gently around you. There is nowhere you need to rush tonight. The arguments have been going on for a century and a half. They will continue long after tonight. All we need to do is breathe and listen and wonder. Take a moment and really build the image. The enormous head, so disproportionately large it seems almost comic from the front but terrifying from the side. The tiny arms, perpetually debated, perpetually mocked, perpetually mysterious in their exact function. The deep chest, the long tail held out behind for balance, the massive hind legs. Now ask yourself a simple question. How fast could it run? This is not a simple question at all. It is, in fact, one of the most intensely debated topics in all of dinosaur science, and the reason it matters goes far beyond mere curiosity about how dangerous the most famous predator in Earth's history actually was. Speed tells us about metabolism. It tells us about anatomy. It tells us about ecological role. whether a predator was an active pursuit hunter or an ambush specialist, whether a prey animal had any hope of escape or was simply waiting for an inevitability. Speed tells us about the structure of entire ecosystems, about who ate whom and how, about the daily rhythms of life in ancient worlds. And we have been arguing about it vigorously for a very long time. The early view of Tyrannosaurus speed was shaped by the assumptions we discussed in the last act. The assumption of cold-bloodedness, of metabolic sluggishness, of an animal more like a large crocodile than like an active, energetic predator. In this framework, Tyrannosaurus was imagined as a slow mover, perhaps more of a scavenger than a hunter, relying on carrion rather than actively chasing down prey. The scavenger hypothesis had a surprisingly enthusiastic advocate in a scientist named Jack Horner, who made some of the most important dinosaur discoveries in American paleontology history, including the first dinosaur nests and eggs found in North America. Horner argued with considerable passion, and some supporting anatomy, that Tyrannosaurus was primarily a scavenger. Its tiny arms couldn't grapple with struggling prey. Its forward-facing eyes, often cited as evidence of predatory binocular vision, could have other explanations. Its enormous olfactory bulbs, the parts of the brain dedicated to smell, suggested an animal that found food by tracking scent, which is consistent with scavenging. The debate this ignited was fierce. Other researchers countered with their own anatomical arguments. Yes, the arms were small, but the jaw was enormous and the bite force was extraordinary. The strongest bite force of any terrestrial animal ever calculated, capable of crushing bone. Yes, the olfactory bulbs were large, but many dedicated predators have excellent senses of smell. And the forward-facing eyes, providing binocular overlap for depth perception, are characteristic of hunters across the animal kingdom, from owls to lions to human beings. Then came the speed calculations. Biomechanical analyses of the T-Rex skeleton began in earnest in the 1990s, using techniques borrowed from engineering and biomechanics to estimate how the animal moved. These studies looked at bone structure, muscle attachment points, leg proportions, and center of mass, and tried to calculate the maximum sustainable running speed of a full-grown Tyrannosaurus. The results were deeply controversial. Some early analyses suggested that T-Rex could have run at speeds of 25 to 45 miles per hour, fast enough to catch any prey animal in its ecosystem. This was exciting news for the predator hypothesis, but troubling news for the biomechanists because when they looked more carefully at the bone structure, they found a problem. To run at those speeds, a Tyrannosaurus would have needed enormously powerful leg muscles, muscles so large that they would have constituted an unrealistically high percentage of the animal's total body mass. The math didn't quite work. The legs that made T-Rex such an impressive standing animal didn't have enough surface area on the bones for the muscle attachments that would be required for truly high-speed running. Revised analyses began lowering the estimated maximum speed. Rather than a sprinter, T-Rex started to look more like a fast walker, an animal capable of sustained ground-covering movement at maybe 12 to 15 miles per hour, with perhaps brief bursts of something faster, but probably not the 45-mile-per-hour predator of popular imagination. Then, a study using computer modelling, published in 2017, went further. It concluded that a full-grown Tyrannosaurus probably could not run in the traditional sense at all, that the forces generated by a full-speed running stride would have stressed the leg bones to the point of fracture. T-Rex, this analysis suggested, moved in a fast walk at maximum effort, never achieving a true running gait where both feet leave the ground simultaneously. The popular science media had a field day. Headline after headline proclaimed that T-Rex was actually slow, that the king of dinosaurs was a plodding walker rather than a fearsome sprinter. But other researchers pushed back immediately. They pointed out that the computer model made assumptions about bone density and muscle architecture that may not have been accurate. They noted that fast walking can be remarkably efficient. Some modern birds achieve impressive speeds through walking rather than running, and theropod dinosaurs were the ancestors of birds after all. They argued that the relevant question wasn't whether T-Rex could sprint, but whether it could cover ground fast enough to catch prey, which it almost certainly could, if the prey was large and not particularly fast. And then came the trackway evidence. Fossilized trackways, preserved footprints in ancient rock, are one of the most valuable and most frustratingly incomplete tools in paleontology. A trackway tells you stride length, step width, and with careful calculation, something about the speed of the animal that made it. The formula is elegant. Longer strides relative to leg length generally indicate faster movement. Tracks attributed to large theropods show stride lengths consistent with brisk, purposeful movement. Not panicked sprinting, but not leisurely strolling either. The picture that emerges is of an animal that moved with deliberate efficiency, covering ground steadily, probably conserving energy for the moments when it needed to surge. This picture, efficient, purposeful, not a sprinter but not slow either, is broadly consistent with what we see in modern large predators. Lions don't sprint after prey unless the ambush is close enough to succeed. They save their high-intensity effort for a carefully chosen moment. Crocodiles are ambush hunters for similar energetic reasons. If T-Rex operated on similar principles, it doesn't need to have been a marathon runner to have been an effective predator. But the debate is far from settled. New studies appear regularly with refined estimates, different methodologies, different conclusions. The argument about T-Rex speed is ongoing, and if the argument about the most famous dinosaur in history is still active and unresolved, you can imagine how complex the speed debate becomes when extended across the entire 200 million year span of dinosaur evolution, across hundreds of species ranging from the size of a chicken to the size of a house. Small theropods are broadly agreed to have been fast. Creatures like Velociraptor, which was actually turkey-sized in reality, rather than the man-height creature of popular films, were probably capable of impressive speed relative to their size. Their anatomy is bird-like in many respects, and modern birds can be remarkably fast. Roadrunners hit 25 miles per hour. Ostriches reach 45. The biomechanics of small theropods are consistent with similar capabilities, but Velociraptor speed is itself argued. How fast is too fast? How much of their anatomy was designed for speed versus for other purposes, grappling with prey, climbing, maneuvering in dense vegetation? The arguments continue at the level of specific species and specific ecological contexts. The large sauropods, those long-necked giants that represent the other extreme of dinosaur body size, present completely different speed questions. How fast could an animal the size of Argentinosaurus actually move? Argentinosaurus, discovered in Patagonia, may have been the largest land animal that ever lived. Estimates range from 70 to 100 tons, though these estimates are themselves heavily argued because the animal is known from fragmentary remains. An animal that large moves slowly. This is a simple consequence of physics. The larger an animal is, the more its limbs must support relative to their cross-section, and the more carefully it must place its feet to avoid catastrophic injury. Trackways of large sauropods suggest maximum speeds of perhaps 4 to 5 miles per hour. A brisk walking pace for a human, but for an animal that size, a reasonable and sustainable gait. But even here there are arguments. Were these animals capable of faster movement over shorter distances? Could a young sauropod, before it reached full size, run from predators? At what size did the biomechanical constraints of enormous mass begin to override the advantages of scale? The speed debate is not just about numbers. It is about the lives these animals lived. An animal's speed tells you about its ecology, its behavior, its relationships with other species. It tells you whether a predator was a pursuer or an ambusher. It tells you whether prey species had any hope of escape or were simply relying on other defenses. Armor, horns, size, group living. All of these questions are still being argued. And beautifully, the arguments are getting more sophisticated every year. New technologies are being applied to the problem. Computer simulations of muscle and bone, laser scanning of fossil surfaces to capture detail invisible to the naked eye, new mathematical models of locomotion borrowed from engineering and physics. The picture of dinosaur movement is slowly becoming clearer, but slowly and with constant revision. Let the image of T-Rex drift through your mind one more time. Enormous, ancient, moving through a landscape we can barely imagine, under a sky we'll never see. Was it running? Was it walking? Was it closer to a lion or closer to a very large, very dangerous crane? The argument continues, and isn't that a beautiful thing, in its own quiet way? Let your thoughts slow down now. Let the images of ancient movement blur softly at the edges. You've been thinking about extraordinary things tonight, and your mind deserves rest as much as your body does. Breathe in slowly, breathe out slowly. We'll keep going. Here is something remarkable to consider, as you lie comfortably in the dark tonight. The world inside a dinosaur's head, the sights it saw, the sounds it heard, the smells that reached its brain and triggered responses we can only guess at, all of this is recoverable to some degree. Not perfectly, not completely, but partially tentatively through the patient application of science to ancient bones and ancient chemistry and the careful logic of comparison. And every tentative recovery of a piece of that inner world has been argued about extensively, sometimes bitterly, always passionately. Let's start with colour. For most of the history of paleontology, the question of dinosaur colour seemed almost unanswerable. Colour is stored in soft tissues, pigments in skin and feathers and scales, not in bones. Bones preserve, soft tissues generally don't. So the question of what colour a Stegosaurus was, or whether T-Rex had stripes, or whether sauropods were uniform grey-brown or patterned like modern birds, seemed destined to remain forever in the realm of artistic speculation. And for a long time, that is exactly where it lived. Museum artists and nature illustrators made their best guesses, influenced by the colours of modern large animals. Elephants and rhinos tend toward grey and brown, so perhaps large dinosaurs did too. Maybe some were patterned for camouflage. Maybe some had display colours on crests or frills, but these were guesses. Educated guesses, but guesses. Then came melanosomes. Melanosomes are tiny structures inside cells that produce and store pigment. In feathers, they come in specific shapes that correspond to specific colours. Elongated melanosomes produce darker colours, round ones produce different tones, and the arrangement of different melanosome types creates the rich palette of modern bird feathers. Crucially, melanosomes can preserve. They are small and dense enough that they sometimes survive the fossilization process, embedded in the impressions left by ancient feathers and skin. In 2010, researchers published a paper that sent a quiet shock through the paleontological community. They had analysed melanosomes preserved in the feathers of Sinosauropteryx, a small feathered dinosaur from the Yixian Formation in China, and determined that the animal had had a reddish-brown coat, possibly with alternating dark and light banding on its tail. This was the first time a specific colour had been reconstructed for a dinosaur with any scientific confidence. It was a moment of genuine discovery. A creature that had been extinct for 125 million years had just told us, through the microscopic structures in its fossilised feathers, what colour it had been. The arguments that followed were immediate and energetic. Some researchers questioned whether melanosome shape could reliably be used as a proxy for colour after 125 million years of preservation. The fossilization process is complex, and there were genuine questions about whether the structures being identified as melanosomes might be something else entirely. Bacteria, perhaps, that had colonized the feather impressions during fossilization and been misidentified. These were not frivolous objections. They were serious scientific questions about methodology and interpretation. And they were answered, painstakingly, through additional studies comparing melanosome structure in fossilized versus modern feathers, through chemical analysis confirming the presence of melanin rather than bacterial contamination, through studies across multiple specimens and multiple species. The melanosome method has now been applied to a growing number of feathered dinosaurs, with results that are cautiously but increasingly trusted by the research community. A partial colour reconstruction of Anchiornis, another small feathered dinosaur, suggested a bird-like pattern with a reddish crest and black and white striped wings. Microraptor, a four-winged gliding dinosaur, showed evidence of iridescent black feathers, similar to a modern raven or starling. But these are all small feathered dinosaurs. The colour of large, scale-covered dinosaurs, the tyrannosaurs, the ceratopsians, the sauropods, remains beyond current reach. We can speculate based on the colours of modern large animals and modern large reptiles, but we cannot yet read the melanosomes of animals that left no feathers behind. And so the argument continues at two levels: the methodological argument about how reliable the melanosome technique is, and the deeper argument about what the colours of feathered dinosaurs tell us about the colours of other dinosaurs. Now consider sound. What did dinosaurs sound like? This question is guaranteed to make any paleontologist smile slightly, because it is such a wonderful question with such a frustratingly incomplete answer. The sounds of Jurassic Park, those enormous roars, the throaty bellows, the deafening calls, are almost certainly wrong. They were created by sound designers for dramatic effect, borrowing from the vocalizations of large mammals. But dinosaurs were not large mammals. They were theropods, the group that gave rise to modern birds, and birds do not roar. Birds vocalize through a structure called the syrinx, a vocal organ located at the base of the trachea, different from the larynx that mammals use. The syrinx is a sophisticated biological instrument that produces the extraordinary range of bird calls, from the lowest booming of an emu to the highest whistle of a warbler. Its soft tissue means it doesn't preserve in fossils. We cannot directly study the syrinx of a theropod dinosaur, but we can study the skull. In 2016, a remarkable paper described the first known syrinx from a dinosaur, not a theropod, but a bird-like dinosaur called Vegavis, which lived at the very end of the Cretaceous period. The fossilized syrinx suggested the animal was capable of duck-like sounds, hoots and honks rather than roars or tweets. This is exciting but limited evidence. Vegavis was a bird, essentially, living at the tail end of dinosaur evolution. What its syrinx tells us about the vocalizations of non-avian dinosaurs from hundreds of millions of years earlier is not straightforward. Other researchers have pointed to skull structure as a guide. The elaborate crests of hadrosaurs, those duck-billed dinosaurs with hollow head structures, have been analysed acoustically. In the most famous case, the crest of Parasaurolophus, researchers have used CT scanning and computer modelling to reconstruct the internal passages of the crest and calculate what sounds might have resonated through them. The results suggest deep, resonant, low-frequency sounds, something like a trombone or a didgeridoo, not the sharp chirping of a songbird or the roar of a lion, something longer, deeper, more mournful. This interpretation has been disputed. The acoustic modelling depends on assumptions about the internal structure of the crest's soft tissues which don't preserve. The resonant frequencies calculated by the model might be correct, or they might reflect the assumptions built into the model more than the actual biology of the animal. Other hadrosaur researchers have pointed to a completely different line of evidence. Crocodilians, the closest living relatives of dinosaurs other than birds, communicate partly through infrasound. Vibrations below the range of human hearing, they create visible patterns on the surface of water during courtship displays. If dinosaurs used similar low-frequency communication, the sounds would have been felt as much as heard, a deep subsonic presence that we would have to experience in our bones rather than our ears. The arguments about dinosaur sound are ongoing, and likely to remain so until methods for detecting vocalization in fossil remains improve dramatically. And then there is vision. Dinosaur eyes are well preserved in some cases as bony structures called sclerotic rings, rings of small bones that supported the eyeball in life. From these, researchers can estimate eye size and, with careful analysis, something about visual capabilities. Many theropods show large, forward-facing eyes consistent with predatory binocular vision. Herbivores often show eyes positioned more to the sides of the skull, giving wider fields of view for detecting approaching predators. This makes ecological sense and is broadly consistent with the patterns we see in modern predators versus prey animals. But the finer details of dinosaur vision are argued vigorously. Could theropods see colour? Almost certainly. They were closely related to birds, and most birds have excellent colour vision, superior to humans in some respects. But what colours could they see? Could they see into the ultraviolet as some modern birds can? Could they see in the near-infrared? These questions can be partially addressed by studying the neural anatomy preserved in fossil skulls. CT scans of dinosaur brain cases can reveal the relative sizes of different brain regions. An enlarged optic lobe suggest visual acuity, but the specific wavelengths detectable by ancient eyes remain beyond current methodological reach. The sclerotic rings of some dinosaurs suggest enlarged pupils capable of gathering more light, suggesting at least some species were active in low-light conditions. Were there nocturnal dinosaurs? Crepuscular dinosaurs? Active at dawn and dusk? The argument is alive and unresolved. Smell is perhaps even more revealing. The olfactory bulbs, the parts of the brain dedicated to processing scent, are sometimes preserved in fossil brain cases, and their size relative to the total brain gives a crude but real indication of olfactory capability. Tyrannosaurs, as we mentioned earlier, had extremely large olfactory bulbs. They could almost certainly smell extraordinarily well. This fits both the active predator and the scavenger hypothesis, and so it cannot alone resolve that debate. What it does tell us is that dinosaurs lived in a world of scent that was at least as rich and complex as the world we experience visually. They knew their environment through their noses in ways that we can barely imagine. A Tyrannosaurus standing at the edge of a Cretaceous forest could probably smell the blood of an injured animal from miles away. It could probably distinguish individual members of its own species by scent. It may have navigated its territory partly by the chemical messages left behind by other individuals, the way modern mammals and reptiles do. This olfactory world, this invisible landscape of scent and chemical communication, is one of the most interesting and least explored frontiers of dinosaur science, and it is, naturally, argued about. Some researchers argue that the large olfactory bulbs of tyrannosaurs tell us little about actual behavioural reliance on smell. Brain size correlates imperfectly with behavioural complexity in modern animals, and ancient brain organisation may have been different in ways we can't fully reconstruct. Others argue that the olfactory evidence is our best window into the sensory experience of these animals and should be taken seriously. The argument continues. Take a moment now to let all of these sensory images drift through your imagination. Dinosaurs with colours we are only beginning to recover. Dinosaurs producing sounds that shook the air at frequencies below human hearing. Dinosaurs moving through a world of scent as detailed and legible to them as a text is to us. How alien that world would feel to a modern human. And yet how familiar in its fundamental logic, animals sensing their environment, communicating with their own kind, seeking food and safety and reproduction. The tools are different. The scale is different. But the experience of being alive, of perceiving and responding to the world, has a continuity that bridges even the deepest chasms of time. Let that thought rest gently in your mind as your breathing continues its slow, easy rhythm. You're made of the same fundamental stuff as those ancient creatures. The atoms in your body have been part of living things for billions of years. You are, in the most literal sense, connected to everything that has ever lived, including the dinosaurs we're still arguing about. Of all the debates in dinosaur science, perhaps none is more emotionally charged than the debate about intelligence. This is understandable in a way that is worth acknowledging. When we ask whether dinosaurs were intelligent, we are not asking a purely academic question. We are asking, in a sense, about the nature of mind itself, about what kinds of biological structures can produce something recognizable as thought, as intention, as complex behavior. We are asking whether the line between ourselves and the very different animals we share our evolutionary history with is as absolute as we sometimes assume. These are profound questions, and they are, in the context of dinosaur paleontology, argued with extraordinary passion. Let's start with the brain. Dinosaur brains don't preserve. Brains are soft tissue, and soft tissue almost never fossilizes. What we can study are the brain cases, the bony structures that surrounded and protected the brain, and from these, using CT scanning and careful analysis, we can reconstruct the general shape and relative size of the ancient brain. For most of the 20th century, the consensus was that dinosaurs had small brains relative to their body size. This measurement, called the encephalization quotient, or EQ, compares actual brain size to the expected brain size for an animal of that body mass. A high EQ suggests a more neurologically complex animal. A low EQ suggests a simpler one. Most dinosaurs, by this measure, showed low to moderate encephalization. Their brains were smaller, relative to body size, than modern mammals of comparable mass. This was taken as evidence of limited intelligence, a simple, reactive animal that responded to its environment without much in the way of complex cognition. But the argument against this interpretation has grown steadily stronger over the decades. First, the comparison baseline matters enormously. If you compare dinosaur EQs to modern mammal EQs, most dinosaurs look poorly endowed. But if you compare them to modern reptiles, many dinosaurs look quite sophisticated. And since dinosaurs were more closely related to birds and crocodilians than to mammals, using mammals as the comparison baseline may be misleading. Second, and more importantly, brain size is a crude proxy for intelligence at best. Modern animals with relatively small brains can show remarkable behavioural complexity. Ravens, birds closely related to dinosaurs, have brain-to-body ratios that are unremarkable by mammalian standards, yet they solve complex problems, use tools, recognise individual human faces, and engage in what looks very much like deliberate deception. And ravens, remember, are dinosaurs. Evolved dinosaurs, but dinosaurs. Their intelligence is built from the same basic neural architecture as the theropods that produced them. This is the heart of the intelligence debate. When we look at the behavioral complexity of modern birds, and birds show some of the most sophisticated behaviors in the animal kingdom, including tool use, cultural learning, long-term planning, and what appears to be rudimentary theory of mind, and we acknowledge that these abilities evolved from theropod ancestors, the question of how intelligent those ancestors were becomes genuinely difficult to answer from a position of assumed simplicity. Were non-avian dinosaurs as intelligent as modern ravens and crows? Almost certainly not. The specific neural adaptations that make corvids so cognitively impressive evolved within the bird lineage after the non-avian dinosaurs went extinct. But were they more cognitively complex than a modern crocodile? Possibly. Were they capable of basic problem-solving, of individual recognition, of some form of social learning? The arguments are ongoing, and they are complicated by a new and rapidly evolving field: dinosaur behavior. Fossil evidence for dinosaur behavior is rare and precious when it appears. Trackways showing multiple individuals moving in the same direction at the same time have been interpreted as evidence of social movement, herding, or group travel. Nesting sites with multiple nests clustered together suggest colonial nesting behavior, similar to modern seabirds. Fossil bone beds, sites where the remains of many individuals of the same species are found together, have been interpreted as evidence of catastrophic events, a drought or flood that killed an entire population, or as evidence of pack behavior, multiple individuals killed together because they lived and hunted together. The pack hunting hypothesis is perhaps the most argued aspect of dinosaur behavior. The famous opening sequence of the Jurassic Park films, velociraptors hunting cooperatively, coordinating their movements, using intelligent flanking strategies to trap prey, was inspired by a legitimate scientific hypothesis. Jack Horner and other researchers had pointed to the Deinonychus bone beds of Montana, where multiple individuals of this sickle-clawed predator were found associated with the bones of a much larger herbivore, as evidence that Deinonychus hunted in coordinated groups. The reasoning seemed compelling. A single Deinonychus, at roughly 11 feet long and 150 pounds, would have found it very difficult to bring down a Tenontosaurus, the herbivore found with these Deinonychus remains, which could reach 20 feet in length and weigh over a ton. Multiple Deinonychus working together, the hypothesis went, could have overwhelmed prey much larger than any individual could handle. But the pushback was significant. Other researchers pointed out that bone beds don't necessarily indicate cooperative hunting. Modern Komodo dragons will gather around large prey in what looks like pack behavior, but is actually independent opportunism. Each individual is simply attracted to the same food source and eating independently. There is no coordination, no division of roles, no shared strategy. A Deinonychus bone bed might mean the same thing. Multiple individuals attracted to the same prey item or the same carcass, not a coordinated hunting team. The presence of multiple predators at one kill site doesn't prove they were working together. Furthermore, some researchers have argued that the ratio of Deinonychus individuals to prey remains in these bone beds suggests that the predators were being killed alongside their prey, perhaps by the prey's defensive kicks, rather than successfully overwhelming it through teamwork. If pack hunting was so effective, why are the predators dying too? The debate has never been resolved. Modern interpretations of Deinonychus ecology range from active pack hunter to opportunistic scavenger to solitary ambush predator that sometimes gathered at large carcasses. Each interpretation has its advocates and its evidence, and the larger question of dinosaur social behavior extends far beyond Deinonychus. Were hadrosaurs herd animals? Trackway evidence strongly suggests they moved in groups, and the colonial nesting sites found in Montana by Jack Horner, which showed evidence of parental care. With young animals remaining in the nest while adults brought food, tell us something profound about hadrosaur social complexity. These were not simple, solitary animals. They lived in communities, cared for their young, almost certainly communicated with each other through those resonant crests. Were sauropods social? Again, trackways suggest group movement. Did they form herds for protection, like modern elephants? Did they have complex social hierarchies? Did younger animals learn from older ones? We don't know. We argue about it. Were tyrannosaurs solitary hunters, like most modern large cats, or did they hunt in groups, like lions? A bone bed found in Alberta in 2014 contained the remains of 3 different-sized Albertosaurus individuals, the same species but different ages, possibly representing different life stages. This has been interpreted as evidence of multi-generational group hunting or social structure. Others interpret it as coincidence. The argument continues. And then there is the parental care debate. Jack Horner's discovery in the 1970s of hadrosaur nests in Montana, nests showing evidence of multiple clutches, of young animals that were too large to have just hatched, meaning they stayed in the nest after birth, and of eggshell fragments suggesting parents were bringing food, was transformative. He named the species Maiasaura, the good mother lizard, and the evidence of dinosaur parental care became one of the most important arguments for dinosaur behavioral complexity. But the interpretation of nesting evidence is itself argued. How much parental care did different species provide? Were the young in the nest being actively fed, or simply remaining near the nest as a safe location? Did parental care end quickly, or were family bonds maintained over longer periods? Comparisons with modern crocodilians, which are among the most attentive reptile parents, guarding nests and even helping hatchlings reach water, suggest that parental care in dinosaurs was probably more widespread and sophisticated than early researchers assumed. But the specific forms it took remain unclear for most species. The intelligence and behaviour debates are personal in a way that other paleontological arguments are not. They ask us to imagine what it was like inside the experience of these animals, to imagine a Maiasaura mother watching over her nest in the Cretaceous heat, responding to the calls of her hatchlings, to imagine a group of Deinonychus moving through ancient forest with a shared purpose, or not, as the argument continues. These imaginings are not indulgent, they are the point. Understanding what kind of creatures dinosaurs were, not just their anatomy but their lives, is the ultimate goal of paleontology. And the fact that we are still arguing about it, still pushing toward a fuller picture, means the understanding is still growing. Let these images settle over you gently. The good mother lizard in her nest, the pack of hunters maybe in the forest edge, the herds moving across ancient floodplains, communicating through low resonant calls that vibrated the very air. What a world it was! What worlds within worlds, argued about and partially recovered and never fully known. That is the beauty of what scientists do, and it is the beauty of what we're doing here tonight, reaching back through unimaginable time, recovering fragments of ancient experience and wondering. Let your wondering be gentle now. Let it float up and away like smoke. You don't need to hold on to these thoughts. They'll be here when you come back to them. For now, just breathe. 66 million years ago, on a day that began like any other day in the late Cretaceous period, something happened above what is now the Yucatan Peninsula of Mexico. A rock fell from the sky. Not a small rock, not a meteorite that leaves a crater the size of a city block. This was an asteroid, a piece of ancient solar system debris between 6 and 10 miles across, and it was travelling at somewhere between 12 and 20 miles per second when it hit. The impact released energy equivalent to roughly 100 million nuclear bombs. The explosion was visible from space. The shockwave travelled around the planet multiple times. The heat pulse ignited forests thousands of miles away. The material thrown into the atmosphere darkened the sky for months, then years, blocking sunlight and collapsing the food chains that every large land animal depended on. This is, broadly speaking, what killed the dinosaurs. Or rather, what killed the non-avian dinosaurs was the birds survived, and they are dinosaurs, which means that in a technical sense, dinosaurs are not extinct at all. The bird outside your window tomorrow morning is a dinosaur, but you knew this story already, more or less. What you may not know is how violently and exhaustively it has been argued about. The asteroid hypothesis, now usually called the impact hypothesis, was not always the consensus view. In fact, when it was first proposed in 1980 by physicist Luis Alvarez, his geologist son Walter Alvarez, and their colleagues Frank Asaro and Helen Michel, it was considered deeply radical and was resisted strongly by the majority of the paleontological community. The Alvarez team's evidence was chemical. They had found an anomalously high concentration of iridium, a metal rare in the Earth's crust but relatively common in asteroids, in a thin layer of clay at the geological boundary between the Cretaceous and the Paleocene periods. This boundary, called the KPG boundary or the KT boundary in older literature, is the exact geological moment when the dinosaurs disappear from the fossil record. The iridium, the Alvarez team argued, could only have come from a massive asteroid impact. The thin clay layer represented the fallout from that impact, the vaporized asteroid and the rock it had excavated from the Earth. Spread around the entire planet by the blast and the subsequent atmospheric circulation. The reaction from many paleontologists was skeptical at best, and openly hostile at worst. Part of the resistance was simply professional. Physicists and chemists were telling geologists and paleontologists what had happened in their field, at the boundary between two of the most important geological periods in the history of life. This was not welcomed by everyone, but part of the resistance was substantive. Paleontologists who had spent their careers studying the KPG boundary knew that the dinosaur extinction was not as sudden as the impact hypothesis implied. The fossil record showed a decline in dinosaur diversity throughout the final stage of the Cretaceous, the Maastrichtian age, that began millions of years before the impact layer. Some researchers argued that dinosaurs had already been in decline, and the impact was simply the final blow to a group already struggling. Others pointed to the Deccan Traps, a massive volcanic province in what is now India, which was erupting explosively during the last million years of the Cretaceous. Could the extinction have been caused primarily by volcanism, as previous extinctions had been? Could the impact have been a coincidence, occurring after the dinosaurs were already doomed? The debate between impact advocates and volcanism advocates was one of the most intense in the history of paleontology. It ran for decades, with new evidence arriving continuously on both sides. The discovery of the Chicxulub crater beneath the Gulf of Mexico and the Yucatan Peninsula in the early 1990s was a major milestone. Here was the actual impact site, a structure roughly 110 miles across, buried under miles of sediment. Detectable only through geophysical techniques. The dating of the crater matched the KPG boundary precisely. The physical evidence for a massive impact at exactly the right time was now overwhelming. But the volcanism argument didn't disappear. Instead, it evolved. New studies of the Deccan Traps showed that the most intense phase of volcanism coincided with the Chicxulub impact within a geological eye blink, raising the intriguing possibility that the impact may have actually triggered or intensified the volcanism, perhaps through global seismic effects. If this is correct, then the extinction was caused by both, impact and volcanism working together in a catastrophic combination. The current state of the extinction debate is nuanced in ways that the simple asteroid killed the dinosaurs story doesn't capture. The impact was real, the evidence is overwhelming, but the Deccan volcanism was real too, and the question of whether non-avian dinosaurs were already declining before the impact, or whether they were doing well right up to the moment of impact, is still genuinely argued. Some researchers, analysing dinosaur species diversity in the last few million years of the Cretaceous, see a clear pattern of decline. Fewer species, smaller geographic ranges, less ecological diversity. This suggests a group already in trouble when the asteroid arrived. Other researchers, often working with different datasets and different statistical methods, see no such decline. They see dinosaur diversity holding steady or even diversifying right up to the boundary layer. In their analysis, the extinction was abrupt and total, caused entirely by the impact and its aftermath, with no prior decline to speak of. Both groups have published peer-reviewed papers, both have responded to criticisms, both remain largely unpersuaded by the other's arguments. The argument also extends to what actually killed dinosaurs in the aftermath of the impact. The initial blast and heat pulse were devastating but localized. The global effects, the impact winter, the collapse of photosynthesis as sunlight was blocked, the acid rain, as sulfur-bearing rocks were vaporized and the compounds reached the upper atmosphere, these took months to years to fully develop. What happened to the survivors in those months? How quickly did temperatures drop? How completely did photosynthesis shut down? Different models of the impact aftermath give different answers, leading to different estimates of how long it took for the extinction to play out. Some models suggest the impact winter lasted only a few years. Terrible, catastrophic, but geologically brief. Others suggest decades of reduced sunlight and collapsed food chains. The difference matters enormously for understanding why some lineages survived and others didn't. Why did birds survive when other theropods didn't? This is one of the most interesting specific arguments within the broader extinction debate. Birds were small, able to live on seeds and detritus that persisted after the collapse of larger food chains. They may have been endothermic in ways that other dinosaurs weren't, or more strongly so, giving them an advantage in the cold impact winter. They may have had behavioural flexibility that allowed them to exploit a wider range of food sources. But other small dinosaurs also existed at the time and did not survive. Why them and not birds? The argument about the specific filter that selected birds for survival while eliminating their close relatives is ongoing. Similarly, why did crocodilians survive? Why did lizards and snakes? Why did small mammals? The extinction was discriminatory in ways that are not fully explained by simple models of temperature drop or food chain collapse. Something about the biology of survivors distinguished them from the biology of victims, and teasing apart that something is an ongoing research program. And perhaps the most haunting argument of all, were there dinosaur survivors, not birds, which everyone acknowledges. But non-avian dinosaurs, were any of them hanging on into the Paleocene? A few fragmentary fossils have been found above the KPG boundary layer, in rock that dates to the early Paleocene. These are disputed. Most researchers believe they represent reworked fossils, bones that had been deposited in Cretaceous sediments and were later eroded and redeposited in younger rock, creating a false impression of post-impact survival. But the possibility of actual Paleocene survivors is not entirely dismissed, and the arguments over these specimens are detailed and technical, and very much ongoing. 66 million years of silence. 66 million years since the last non-avian dinosaur left a footprint in mud, since the last tyrannosaur jaw closed on prey, since the last hadrosaur called across a Cretaceous floodplain, and we're still arguing about exactly how that silence began. There is something deeply moving about that, about the fact that human beings, who have existed for an eye blink compared to the dinosaurs, care enough about these lost creatures to keep the argument alive, to keep looking for new evidence, to keep refining our understanding of what happened on that day and in the months and years that followed. The extinction arguments are not morbid. They are a form of remembrance, a way of saying that these animals mattered, that their stories are worth understanding, that the silence they left behind is worth trying to fill with knowledge. Rest in that feeling for a moment, the weight of deep time, the patience of scientific inquiry, the quiet persistence of curiosity across generations of researchers, each building on the work of those who came before. This is one of the finest things human beings do, and you are part of it simply by listening. There is a quality that the best paleontologists seem to share, and it is not confidence, it is comfort with uncertainty. Because paleontology, more than almost any other science, operates at the edge of what can be known. Every conclusion is provisional, every reconstruction is a best estimate, every argument is subject to revision the moment new evidence arrives from the ground, and the evidence keeps arriving. The pace of dinosaur discovery has accelerated dramatically in recent decades. New species are being named at a rate that would have astonished the paleontologists of the 19th century. In some years, more than 50 new dinosaur species are formally described. New fossil sites are being found on every continent, including Antarctica. New technologies are revealing details about known fossils that earlier techniques couldn't access. And with every discovery, new arguments begin. Let's travel to Argentina, to the sun-baked badlands of Patagonia, where the rock formations of the Neuquén Basin preserve an extraordinary record of the Cretaceous world, a world that was part of Gondwana, the southern supercontinent, separated from the northern landmasses of Laurasia by an ancient sea. From these formations, over the past 30 years, some of the most astounding dinosaur discoveries in history have emerged. In 1993, a farmer named Guillermo Heredia found a bone weathering out of a hillside on his ranch. He reported it to a museum, and the excavation that followed eventually revealed the remains of what is now recognized as one of the largest dinosaurs ever found, Argentinosaurus, a titanosaur sauropod of almost incomprehensible size. The problem with Argentinosaurus is that the known material is fragmentary. Several vertebrae, some limb bones, pieces of rib. From these fragments, researchers have attempted to estimate total body length and mass, and the estimates have varied enormously. Some calculations put Argentinosaurus at 70 tons, Others suggest 100 tons. Some researchers have argued for even higher figures. Others have urged caution, noting that extrapolating total size from partial remains is notoriously unreliable. The argument about the size of Argentinosaurus is itself a microcosm of a larger methodological debate. How do you reliably estimate the mass of an animal from fossil bones? Different methods, volumetric modelling, bone scaling, comparison with living relatives, give different results. The uncertainty ranges in mass estimates for many large dinosaurs span dozens of tons. This matters not just for satisfying curiosity about how big things were. Mass estimates feed into calculations about metabolism, movement, feeding ecology, and thermal biology. Get the mass wrong, and every downstream calculation is compromised. From the same Patagonian formations, subsequent discoveries have produced other candidates for the title of largest dinosaur. Patagotitan majorum, described in 2017, was calculated by its describers to have massed around 76 tons, making it the largest dinosaur confirmed by reasonably complete remains. But within weeks of the paper's publication, other researchers were publishing critiques of the mass estimation methodology. The argument about the largest dinosaur ever to walk the Earth is, at this moment, unresolved. And it is a beautiful argument, because it is essentially an argument about the outer limits of biological possibility on this planet. How large can a land animal get? What constraints, structural, physiological, ecological, set the ceiling on body size for terrestrial vertebrates? The sauropods pushed those limits further than anything else in Earth's history, and we are still arguing about exactly how far they pushed. Now travel north, to Montana and Alberta, and the other fossil-rich badlands of North America, where the Hell Creek and Judith River formations have been producing extraordinary dinosaur fossils for over a century. Here the arguments take a different form. In 2014, a paper was published describing what its authors claimed was a new species of tyrannosaur, a previously unknown large predator from the Two Medicine Formation of Montana, named Nanuqsaurus hoglundi. The announcement generated considerable excitement. A new tyrannosaur is always news. But the skepticism arrived quickly. Other researchers examined the specimen and argued that what had been described as a new species was actually a juvenile Tyrannosaurus rex, that the features used to distinguish the new species were developmental, reflecting the immature state of the individual rather than the characteristics of a distinct species. This is one of the most persistent sources of argument in dinosaur paleontology, the juvenility problem. Dinosaur growth rates, as we now know, were remarkable. Many species grew from hatchling to full adult size in a matter of years, not the decades that large mammals require. This means that a juvenile and adult of the same species could look dramatically different. Different proportions, different bone textures, different surface features. The danger, which has been demonstrated repeatedly, is that juvenile individuals can be mistakenly described as new species. The number of species that have subsequently been determined to be juveniles of previously known animals, invalidating years of published research, is significant. Jack Horner, who has spent decades working on Hell Creek dinosaurs, has been one of the most vocal advocates of this skeptical approach. He and his colleagues have argued that several famous dinosaur species, including Triceratops and Torosaurus, two large horned dinosaurs found in the same formations, might not be separate species at all, but different growth stages of the same animal. The Torosaurus argument was particularly dramatic. Triceratops is one of the most iconic dinosaurs, instantly recognizable with its 3 horns and massive frill. Torosaurus is a larger horned dinosaur with a longer fenestrated frill, one with large openings, unlike the solid frill of Triceratops. Horner and his colleague John Scannella proposed in 2010 that Torosaurus was simply what Triceratops looked like when fully mature, that the solid frill of Triceratops changed dramatically in shape as the animal aged, eventually developing the large openings seen in Torosaurus. In this scenario, there was no Torosaurus as a separate species, there were simply old Triceratopses. The reaction from other researchers was immediate and largely skeptical. Critics pointed out that if the two forms were growth stages, you'd expect to find individuals at intermediate stages, Triceratopses partway through the process of developing Torosaurus-style frills. No such intermediates had been found. Furthermore, Both forms were found in the same geological formations, and if Torosaurus was just old Triceratops, you'd expect Triceratops to be absent from the oldest adult size class. But Triceratops individuals of apparently adult size were found alongside what had previously been called Torosaurus. The argument has not been definitively resolved. Most researchers currently favour treating Torosaurus as a distinct species, but the question is still considered open by some. These debates about species boundaries, what counts as a new species versus a growth stage versus a sexual variant versus individual variation, are among the most common and most difficult arguments in dinosaur paleontology. And they matter enormously, because our understanding of dinosaur diversity, of how many species coexisted at any given time, depends entirely on getting species boundaries right. Now move forward in time to the Chinese feathered dinosaur revolution, the Ixian Formation discoveries, which we touched on earlier in the context of colour reconstruction, have generated an extraordinary and ongoing series of arguments about the relationships between dinosaurs and birds, about the origin of flight, and about the diversity of feathered dinosaurs in the early Cretaceous. One of the most contentious specific debates concerns the four-winged dinosaur Microraptor. Microraptor was a small, crow-sized dromaeosaur related to Velociraptor that had long pennaceous feathers on all four limbs. The arrangement suggests the animal was capable of some form of gliding or powered flight. But exactly how Microraptor flew, and what this tells us about the evolution of bird flight, has been argued intensively since the first specimens were described in 2003. The basic question is how Microraptor positioned its hindwings during flight. Different postures produce completely different aerodynamic properties. One hypothesis suggests the hind wings spread out laterally, creating a biplane-like configuration similar to some early aircraft designs. Another suggests the hind wings were positioned more below and behind the body, like a swept-back delta configuration. Wind tunnel experiments with scale models have been conducted. Computer simulations of Microraptor flight dynamics have been run. Anatomical analyses of hip joint structure have been done to determine which configurations were even physically possible. The results have been contradictory. Different groups, using different methods and different assumptions, have reached different conclusions. The argument is genuinely unresolved, and it matters because Microraptor sits at or near the evolutionary origin of bird flight. Understanding how Microraptor flew, or whether it flew at all, as opposed to simply gliding, is a step toward understanding how powered flight evolved in the dinosaur lineage that produced modern birds. The origin of flight debate is itself one of the longest-running arguments in paleontology. Did flight evolve from the ground up, with ground-running dinosaurs developing wing-assisted running before achieving true flight? Or did it evolve from the trees down, with arboreal dinosaurs using gliding as a precursor to powered flight? Both hypotheses have serious advocates, both have anatomical and biomechanical support, and both face significant challenges. The trees-down hypothesis struggles with the question of how proto-wings could have been maintained by selection in a ground-dwelling animal before they were large enough to provide useful lift. The ground-up hypothesis struggles with aerodynamic analyses showing that small proto-wings on a running animal provide negligible benefits and significant costs. Various compromise hypotheses have been proposed. Perhaps flight evolved in animals that were already partly arboreal and partly terrestrial, using their developing wings for both upward leaping and breaking falls from trees. Perhaps flight evolved multiple times in different theropod lineages, following different evolutionary paths. Perhaps the sequence of selective pressures was different from what either the trees-down or ground-up models predict. The argument is ongoing. New fossils from China continue to arrive, each one suggesting new interpretations. The origin of bird flight remains one of the great unsolved puzzles of vertebrate evolutionary biology. These new discoveries, from Patagonia and Montana and Liaoning and dozens of other fossil-rich sites around the world, are not resolving the arguments in dinosaur paleontology. They are, more often, creating new ones, and this is exactly as it should be. Every good scientific argument is a machine for generating better questions. Every answer that emerges from the evidence creates new puzzles at its edges. The sophistication of the arguments in dinosaur paleontology today is evidence not of confusion, but of depth, of a science that has penetrated far enough into its subject to see how complex that subject really is. The arguments will continue for as long as there are people curious enough to have them, which will be, If the last 2 centuries of paleontology are any indication, a very long time indeed. Take a slow breath. Let the images of ancient discovery settle. The bone half buried in Patagonian rock, the feathered impression in fine Chinese mudstone, the trackway stretching across ancient desert. All of these things waiting in the earth for millions of years, patient beyond any human concept of patience. Until the moment they were found, everything we've discussed tonight was waiting, buried and quiet and real, waiting for the curious hands and patient minds that would eventually find it. The waiting is over for these particular bones, but there are millions more still in the earth, millions of stories still untold, millions of arguments not yet begun. Rest in the knowledge of that abundance. It is a beautiful thing. Here is a question that opens onto something vast. What do the dinosaurs tell us about life? Not just about themselves, about their anatomy and their ecology and their extinction, but about life in general, about the principles by which living things evolve, adapt, succeed, fail, and leave their traces in the world. Because the dinosaurs were not just interesting animals, they were, and this sounds dramatic but is accurate, one of the most successful experiments in the history of terrestrial life. They dominated the land for 165 million years. They occupied every major ecological niche available to large land animals. They evolved into forms that pushed the known limits of terrestrial biology in almost every direction. And the arguments about what their success tells us about life are among the most interesting and most far-reaching in all of science. Let's start with an argument about timing. Why did dinosaurs succeed when they did? The Triassic period, when dinosaurs first appeared and then became dominant, is one of the most interesting intervals in Earth's history from an evolutionary perspective. As we described earlier in our stories about the Carnian pluvial episode, the ecological stage was set by a combination of the Permian-Triassic mass extinction, the Triassic recovery, and the subsequent environmental disruptions that cleared the competitive field and allowed a relatively minor group of reptiles to rise to dominance. But the specific reasons for dinosaur success in this context are argued passionately. One school of thought emphasizes contingency, the role of luck and accident in evolutionary history. In this view, dinosaurs succeeded not because they were inherently superior to their competitors, but because they happened to be in the right place with the right body plan when the environmental disruptions of the Carnian pluvial episode knocked back their competitors. It could have been another group that rose to dominance. History turned out the way it did because of a combination of circumstance and opportunity, not because dinosaurs were inevitably destined to dominate. Another school of thought emphasizes competitive superiority. The idea that dinosaurian anatomical and physiological features genuinely made them better at exploiting the available ecological niches than their competitors. In this view, the upright posture, the elevated metabolism, if they had it, the efficient respiratory system that would eventually become the air sac system of modern birds, these gave dinosaurs real advantages that would have led to their dominance eventually, regardless of the specific environmental disruptions of the Triassic. The truth is almost certainly somewhere between these poles. But the relative weighting, how much was luck, how much was advantage, is a matter of genuine scientific disagreement that touches on some of the deepest questions in evolutionary biology. Similar arguments arise about the patterns of dinosaur diversification. For 165 million years, dinosaurs were broadly dominant, but their dominance was not static. Different groups rose and fell within the overall dinosaurian success story. In the Jurassic, the sauropods were perhaps the most ecologically dominant group, their enormous size and efficient digestive systems allowing them to exploit plant resources at a scale no other animals could match. In the Cretaceous, the hadrosaurs and ceratopsians largely displaced the sauropods in the northern continents, while tyrannosaurs replaced earlier large theropod predators. Why did these turnovers happen? Were they driven by climate change, by the evolution of new food resources, particularly the rise of flowering plants in the Cretaceous, which provided new types of vegetation, by competitive displacement, or by purely contingent events? The rise of flowering plants, the angiosperms, is itself one of the most interesting ecological events of the Mesozoic, and its relationship to dinosaur evolution is argued about extensively. Flowering plants provide richer, more concentrated food resources than the conifers and ferns they partly displaced. Did the spread of angiosperms drive the evolution of specialized herbivores? The hadrosaurs with their complex dental batteries, the ceratopsians with their powerful shearing beaks, that could exploit this new resource? Or did the dinosaurs evolve first and the angiosperms simply fill the spaces their herbivory created? This chicken and egg question about the coevolution of dinosaur herbivores and flowering plants is genuinely difficult and genuinely argued. Then there is the question of what dinosaur success tells us about the relationship between body size and evolutionary success. The history of life on Earth shows a general trend toward increasing maximum body size over geological time, a pattern called Cope's rule, after the same Edward Drinker Cope of Bone Wars fame. Animals tend, over evolutionary time, to evolve larger body sizes. Large body size confers certain advantages: better thermal regulation, access to larger food resources, reduced predation risk from most predators. But it also carries costs: higher energy requirements, slower reproduction, lower population densities. Dinosaurs are the most extreme example of this trend in the history of land life. The titanosaur sauropods represent the maximum size ever achieved by terrestrial vertebrates, pushing the physical limits of bone and muscle and cardiovascular anatomy to their absolute boundaries. What do these extremes tell us? Are there fundamental biological constraints on maximum body size that the sauropods were approaching? Could land animals ever evolve to be larger than Argentinosaurus? Or has that limit been essentially reached? The argument about maximum land animal body size is one of those wonderful intersection points between paleontology, biomechanics, physiology, and evolutionary theory. It draws on studies of living large animals, elephants, hippos, rhinos, to establish what we know about the costs and limits of large body size, then extrapolates carefully to the much larger sizes achieved by sauropods. The current consensus, tentative as always, is that sauropods approached but did not quite reach the absolute physical limits of possible land animal size. Something larger might theoretically be possible. But the ecological and physiological constraints that would need to be satisfied make it extremely unlikely that anything larger will ever evolve, assuming large body size were to be selected for again in some future ecosystem. This is speculative. Of course, and speculation is where paleontology and evolutionary biology meet in their most imaginative and most carefully argued forms. Now consider what the dinosaurs tell us about extinction itself. The end Cretaceous extinction is the most famous mass extinction in Earth's history, at least in popular culture, though the Permian-Triassic extinction was by far the more severe event. But the dinosaur extinction is the one that most directly shaped the world we live in, because it cleared the ecological stage for the mammalian diversification that eventually produced us. The argument about mass extinctions in general, their causes, their patterns, their aftermaths, is one of the most active areas of paleontological and geological research, and it has profound implications not just for understanding the past, but for understanding the present. We are living, as paleontologists are now largely in agreement, in the early stages of a sixth mass extinction, an extinction event driven not by asteroid impact or volcanic province, but by human activity. The rate at which species are currently going extinct is estimated to be somewhere between 100 and 1,000 times the normal background rate, the rate at which species naturally go extinct in the absence of catastrophic events. How does this compare to the great extinctions of the past? What can the paleontological record tell us about the likely trajectory and aftermath of the current extinction event? These are not purely academic questions. They are among the most urgent practical questions facing humanity, and they are being argued about extensively, with the full weight of the paleontological record brought to bear on them. Some researchers argue that the current extinction, while serious, is unlikely to reach the severity of the end Cretaceous event or the Permian-Triassic extinction. The causes are different, the timescales are different, and life has resources and refugia that may allow recovery on shorter timescales than those ancient events required. Others argue that the current extinction is potentially more dangerous than historical mass extinctions in certain respects, because it is targeting specific ecological roles rather than randomly sampling the tree of life, and because the removal of key species can trigger cascade effects that collapse entire ecosystems in ways that simple diversity loss might not predict. The dinosaurs, who survived multiple environmental crises during their 165 million year reign, before finally succumbing to an asteroid, offer a complicated lesson. They were enormously resilient, bouncing back from the Carnian pluvial episode, surviving sea level changes and climate oscillations, adapting to the radical ecosystem restructuring brought about by the spread of flowering plants. And then they were gone, at least in their non-avian forms, within a geological instant. What this tells us about resilience and fragility, about the difference between slow change that life can adapt to and sudden change that overwhelms adaptation, this is the most important practical lesson paleontology has to offer, and it is argued about with urgency. The arguments in dinosaur science are not confined to dinosaurs. They reach outward, into ecology and evolutionary biology and climate science and conservation. They ask fundamental questions about how life works, how it fails, and how it recovers. Every argument we've discussed tonight about metabolism, about speed, about behavior, about extinction, is, at a deeper level, an argument about the nature of life itself, about what makes some body plans and physiological strategies successful while others fail, about the relationship between organisms and their environments, about the role of chance versus necessity in shaping the history of living things. These are the arguments that will never be fully resolved, because they are asking questions that go to the very heart of what biology is and what it means, and that is precisely why they are worth having. Let the immensity of the questions settle gently over you. You don't need to answer them tonight. No one will. They are the kind of questions that take generations to approach, that require the cumulative effort of thousands of researchers across centuries. All you need to do tonight is carry the wonder of them into your sleep. The questions will be waiting in the morning. They have been waiting for 200 years. They will wait a little longer. Imagine a paleontologist not yet born. She is perhaps 50 years from now, working at a university that doesn't yet exist, in a field that has been transformed by technologies we can currently only guess at. She has access to tools that make our current methods look as crude as Buckland's drawings of Megalosaurus bones look to us. Tools that can read the chemistry of ancient cells, that can reconstruct the neural architecture of fossilized brains, that can detect the traces of ancient hormones preserved in the crystal structure of bone. She's working on a question that seems unanswerable today. She's working on determining the precise color of a large non-avian theropod, not through melanosome analysis, which only works for feathers and some skin impressions, but through a new technique that extracts pigment chemistry from the mineral matrix of fossil bone and uses it to reconstruct the original colours of the living animal's skin, and she's arguing about it with a colleague. The argument is subtle and specific in a way that the arguments of today would not be, because the gross uncertainties we currently deal with have been resolved, and the science has moved on to finer-grained questions. She and her colleague disagree not about whether the technique works, but about what the results mean in the context of the animal's ecology and behaviour. This is a beautiful thing to imagine. The persistence of argument even as the understanding deepens. The way that answering one question always opens three more, the endless forward motion of curiosity. Because here is what the history of dinosaur science tells us clearly. We will never run out of things to argue about. Every methodological advance creates new questions. Every discovery reveals new complexity. Every answer casts new shadows of uncertainty over adjacent problems. The future of dinosaur science will be shaped by several developing technologies that are already transforming what is possible. Ancient proteins are one frontier. Soft tissue, as we've discussed, almost never preserves in fossils. But there are exceptions. In the early 2000s, Mary Schweitzer, a paleontologist at North Carolina State University, made one of the most controversial discoveries in modern paleontology. She found what appeared to be original soft tissue, blood vessels, bone cells, possibly even proteins, preserved inside the femur of a T-Rex specimen from Montana. The discovery was met with extreme skepticism. Proteins and soft tissues should not survive for 68 million years. The laws of biochemistry, as understood at the time, said that the molecular bonds would have broken down long before. The argument that erupted was fierce, technical, and deeply engaged some of the most fundamental questions in chemistry as well as paleontology. Schweitzer's team defended their findings vigorously. They published additional analyses, identified specific proteins, and developed hypotheses about how the preservation could have occurred, possibly through chemical reactions with iron from the dinosaur's own blood, which created conditions hostile to the bacteria that would normally degrade organic material. Other researchers replicated the findings in other specimens. Ancient proteins were identified in additional theropod bones. the argument gradually shifted from whether the proteins were real to what they could tell us. Ancient proteins can, in principle, tell us about the molecular biology of extinct animals in ways that bone morphology cannot. They can shed light on evolutionary relationships. They can tell us something about physiology and metabolism. They can, if the preservation is good enough, carry phylogenetic information that places extinct animals precisely in the tree of life. The field of paleoproteomics, the study of ancient proteins from fossil remains, is growing rapidly. New analytical techniques are becoming more sensitive. The preservation window for ancient proteins is being pushed further and further back in time. What this will mean for dinosaur science over the next 50 years is impossible to predict precisely, but it seems certain that molecular biology will become an increasingly important tool alongside traditional morphological analysis, and with that expansion of tools will come new arguments about methodology, about interpretation, about what the molecular evidence means in relation to the anatomical evidence. Ancient DNA is a more fraught frontier. The success of ancient DNA research in other contexts, the sequencing of Neanderthal genomes of woolly mammoths, of species that went extinct in historical times, has naturally raised the question of whether dinosaur DNA might someday be recoverable. The honest scientific answer, as of now, is almost certainly not. DNA is far less stable than proteins, and the oldest reliably sequenced DNA currently comes from specimens roughly 1 million years old, nowhere near the tens of millions of years that separate us from non-avian dinosaurs. The science fiction premise of Jurassic Park, dinosaur DNA preserved in amber, is not supported by what we know about DNA degradation rates. But the arguments at the edges of this question are interesting. Could some form of ancient genetic material be preserved in extraordinary circumstances? Could the techniques for recovering degraded genetic material advance far enough to extract something useful from material far older than anything currently analyzable? Most researchers say no. A few say the question is genuinely open. The argument, quiet, technical, and very much ongoing, is about where the limits of biochemical preservation actually are. Isotopic analysis is another rapidly developing frontier. The ratios of different isotopes of elements like carbon, oxygen, nitrogen, and strontium in fossil bone and tooth enamel can tell us about diet, climate, migration patterns, and even individual life histories. A single dinosaur tooth can, in principle, be read like a diary of the animal's life, revealing what climates it experienced as it grew, what foods it ate at different life stages, whether it migrated seasonally. The arguments in this area are currently about calibration, how to correctly interpret isotopic ratios from extinct animals, given that the relationships between isotopes and biology are calibrated on modern animals that may have behaved differently. The method is powerful but requires careful validation, and the validation arguments are ongoing. CT scanning and computer modelling have already transformed the field and will continue to do so. The ability to look inside fossils without cutting them open, to reconstruct three-dimensional digital models of bones and brain cases and inner ear structures to simulate how extinct animals moved and sounded and processed sensory information. These capabilities are still being developed and applied. Future CT analyses will likely resolve some of the current arguments about brain structure and sensory capability. They will certainly generate new ones. The pace of new fossil discovery will continue. New fossil sites are found regularly. The Badlands of Antarctica, which are only accessible for brief windows each year and require enormous logistical effort to excavate, have barely been explored relative to their potential. The deep deserts of Central Asia and Northern Africa remain incompletely surveyed. Parts of South America and Australia that are known to be fossil-rich have not yet been systematically excavated. The diversity of dinosaurs that remains to be discovered is probably very large. Our current picture of dinosaur diversity, the several thousand species formerly named and described, almost certainly represents a small fraction of the species that actually existed. Most dinosaur species died without leaving fossils detectable by human excavation, but many more are out there, waiting in unexplored formations. Each new species brings new arguments, new questions about relationships, about behavior, about ecology. The argument engine has fuel for centuries more, and throughout all of this future discovery and analysis and argument, one thing will remain constant: the basic posture of good science, provisional conclusions, willingness to be wrong, respect for evidence over preference, comfort with uncertainty. These virtues are not uniquely paleontological. They are the virtues of all good science, but paleontology, perhaps more than any other field, makes them visible because the evidence is so incomplete and the questions are so large. You cannot be complacent in paleontology. The Earth keeps producing surprises, and the surprises keep changing the story. For the future paleontologist we imagined at the beginning of this act, the one working with tools we cannot yet envision, arguing about questions we cannot yet frame, the experience will be in its essential character the same as William Buckland's experience in 1824, holding something ancient and fragile and real, looking at it carefully, proposing an explanation, listening to the counter-argument, revising. The technology will be different. The knowledge base will be different. The sophistication of the questions will be almost unimaginably greater, but the argument, the passionate, evidence-driven, intellectually generous argument that advances understanding, will be exactly the same. This is one of the most comforting things about science. Its fundamental character does not change. The tools change, the knowledge changes, the specific debates change. But the method, curiosity, evidence, argument. Revisionist is stable. It has been stable for centuries. It will be stable for centuries more. You can rest in that stability, in the knowledge that the great argument about dinosaurs is being conducted honestly and carefully and with genuine love for the subject, that the people doing it are following the evidence wherever it leads, even when it leads somewhere uncomfortable, even when it overturns their own previous conclusions. The argument is in good hands. Let that thought carry you forward into the final moments of tonight's story. You've travelled a long way, from the earliest bone fragments pulled from Stonesfield limestone, through the bone wars and the cold blood revolution, and the feathered dinosaur discoveries and the extinction debates, all the way to the technologies of the near future. You've heard the arguments, you've felt the weight of deep time and the beauty of sustained inquiry, you've accompanied the dinosaurs from obscurity to discovery to ongoing argument. Now it is time to let all of that settle into the background of your mind, not forgotten, but resting quietly, ready to emerge again when you want it. For now, breathe, deeply, slowly. The argument will continue in the morning. The last light of your waking mind is fading now, softly and slowly, like the last light of an ancient day. Somewhere, 66 million years in the past, the Cretaceous world is settling into evening. Somewhere, a hadrosaur calls across a floodplain. Somewhere, a small tyrannosaur lifts its head and catches a scent on the cooling air. Somewhere, in a nest of carefully arranged vegetation, eggs are warming in the last heat of a Mesozoic afternoon. None of these creatures know they are being studied. None of them know that millions of years in the future, a species that hadn't yet evolved would pull their bones from ancient rock and argue, passionately and carefully and with great love, about what their lives had been. But in some way that is beyond words to express, the arguing is a form of remembrance, a form of gratitude, a way of saying that the great experiment of life, the 4.5 billion year story of organisms finding ways to exist on this remarkable planet, is worth understanding, worth arguing about, worth staying up late and getting up early and spending entire careers trying to understand. You are part of that story. Your atoms have been part of living things for billions of years. You're connected to the dinosaurs not by nostalgia or imagination alone, but by biology, by the unbroken chain of life that reaches from the earliest cells through the ancient oceans, through the Mesozoic forests, through the small mammals that hid from predators and survived the extinction, and eventually, step by cautious step, became us. The arguments will continue. New bones will emerge from the earth. New technologies will read new stories from ancient chemistry. New paleontologists will propose new ideas, and other paleontologists will challenge them, and the understanding will deepen slowly and beautifully, one argument at a time. Tonight, you have been part of that, simply by listening, simply by letting the wonder of it reach you. Now let everything go quiet. Let the images of ancient worlds dissolve at the edges. Let the voices of arguing scientists become a gentle background hum, like distant conversation in a warm room. Let your body be heavy and still. Let your breathing be slow and automatic and peaceful. Somewhere in the earth tonight, A fossil is waiting to be found. A story is waiting to be told. An argument is waiting to begin. But not tonight. Tonight, there is only this. The quiet. The dark. The gentle weight of ancient wonder settling over you like the finest sediment, layer by soft layer. Sleep well. Thank you so much for watching. If you'd like to see more videos like this, please consider leaving a like and subscribing to the channel, as it really helps us continue making more content. Anyways, see you in the next one.